Good morning, everybody, or afternoon. Just going to go in and we're going to run through our chapter 8. So let me switch over and I hope everything's going as well as it can be. So let's switch over and let's get this started. So I hope you're all doing well. I haven't had a chance yet to check on the papers that you've submitted so far, but I do appreciate you all got the groups together, so hopefully that's working out for you. But so basically, I'll hop right into it. We're going to be doing chapter 8 today. And this one is kind of applying a lot of the things that we've done so far. So it's called chapter 8. We're looking at estimation. And as far as what we're going to be doing today, it's combining a lot of the different things that we've seen in the past and applying it to sort of a new formula that's going to be for hypothesis testing. So we're doing chapter 8, estimation. And as far as what we're looking at, I'm going to go review a few of the things we've taken a look at so far and take a look at how this applies to what we're going to be doing today. So going over, let's go in. So applying what we've learned so far, normal curves, as far as, of course, we're doing normal curves. And just as a review, I'm going to take a look at these. The last few times we've been looking at this overall process, normal curve, and remember we have a few of the features of a normal curve. It's standardized, and I pointed out some of these things down here. These scores, and we had z-scores, or they're called standard deviations. And these basically break it up, break the normal curve up into predictable parts. If you look ahead, you can see exactly how much these percentages are and what they make up, what percentage they make up of each section of the normal curve. And based on this, we could then do predictions and apply some estimations on them. So essentially then, we have these normal curves, and they're the foundation of what makes us be able to do the statistics we've been talking about. Again, just the z-scores here. Similarly, when we're talking about using the standard deviations, each of these corresponds to a z-score. Over here, one standard deviation or one z. And we had that whole table we were taking a look at before, which we'll also continue to take a look at as far as the next steps. So let's go back here. So what does this all mean? It's basically a way for us then to take a look at our samples and see how well we did. So previously we had looked at things called parameters and samples. And the parameters, of course, were the whole population, whereas the sample was a subset of that. So the idea being that we want to be able to test how accurate our sample is in relation to the population. So, of course, before, if you recall, we could never actually know the whole population, so it always has to be an estimate. So anything in stats is an estimate. So we're going to combine this idea then to see then, when we pick a sample of 30 students, how likely is it that we got it right? So a big question today, how likely is it we got this stuff right? Circle it. So two terms we need to take a look at. Hypothesis. Just as a reminder, hypothesis is something that's testable. Idea of how two or more concepts are related to each other. So basically anything we've been looking at so far with our research topic, our interest for research, and it's just saying how one concept might be related to the other. The example that I give here is housing costs is one type of thing, and homelessness is another thing. And basically just saying how this one is related to that one. So our argument in this might be saying that housing costs, in California especially, are very high, so they might increase homelessness. So this is our hypothesis. So how do we test that? So first, but before we get into that, there's some assumptions here, and this is important to recall. One, before we can test our hypothesis, we need to have several things in place. One, we need to assume random testing. So as we've said before, one of the main things is stats is random testing because we want to try to eliminate as much bias as possible, meaning that we want to try to make sure that we're not introducing our own perspective into a topic. And some of the examples we did from this were like if I was doing a class satisfaction survey and I only chose the students that were doing the best in my class. So, to pump up my numbers type thing. And we can say that pretty much with any sort of testing we're doing. We want to assume an interval level ratio of measurement. Recall this one as opposed to got nominal, and we also had interval ratio. And the in-between one we had ordinal. So as a range from top to bottom, this one was the most statistical or mathematical, and nominal was basically in name only. So we need to have the most mathematical version of this in order to be able to actually do the stats with it. Remember, we have to assume that it's a sample size of larger than 50 because of our magic number. Remember from before, magic number being 50. And of course, to make these assumptions without them, we wouldn't be able to do our special analysis with them. We use the statistical tools available to us. So it's the basis of anything we're doing with a normal curve. Okay, so step one, then. So we've already talked about what the hypothesis is. And now there's something called a null hypothesis. Okay, so this essentially is like a way to double check our work. And I'll explain what that means in just a little bit. So if we think about what a hypothesis is how two things are related to each other. How two different concepts are related to each other. So I want to highlight that part, the relationship. So in a hypothesis then, when we talk about the relationship in a hypothesis, like we talked about up above, housing costs are related to homelessness. We're saying that housing costs cause homelessness in California. So that's the relationship. Whereas in a null hypothesis, we're arguing that there is no relationship between the two things. Essentially getting at the idea that housing costs are not related to homelessness. So it's all about the relationship when we're talking about these things. Meaning that, and I'll give an example. So let's just go look at this real quick. A null hypothesis is an assertion that there's no relationship between the concepts. So basically then, now this is referring to down here. If you recall that our sample is never going to be 100% right. So like I said, we're never going to be able to ask everybody what they think about something, so we're always guessing. So because we're choosing a sample, we never know whether this is going to be accurate. So there's always a chance that we could happen to choose our sample and that we happen to choose the students that were not the most representative, even though it was random. Okay, so let me let's go look at this one. So example, in our COD satisfaction project, if we were to ask students how satisfied they are with COD, I might pick 30 students for the survey. So I would go ahead and pick 30 students. But basically what this is saying, then what if I happen to pick the 30 students that had straight A's? That every student, they studied every night, and who were able to be students full-time, and they didn't have to balance their student life with work life. We actually might not have an accurate sample. So what we actually might have is in a situation where the students are more satisfied than the general population. Meaning that if we were to use these 30 students to represent the entire College of the Desert, we would actually have a problem where these students are actually more satisfied, therefore the sample would be misleading. So basically what a hypothesis, null hypothesis test then is just testing to see the chances of us choosing a sample that happen to be these, in this case, these 30 students right here that were just very happy with the school. So a way to check that is we run we'll look at what the formula is going to be. But basically the formula is running our assertion, like our sample, our hypothesis, versus what are the chances that we actually just happen to choose 30 students, or whatever the sample size is, that happen to be those students that really like school and were misrepresentative of the rest of the group. So it's basically just testing to see how likely it is, like we said up top, how likely it is we got it right. So basically then, the process is a hypothesis test, testing how accurate our sample is in relationship to the whole population. Okay, so testing how our sample is related to the population. And sorry about the pen feature on this is not working very well. So how related our sample is to the overall population is our goal. So let's look and see what that looks like. So I'm going to go ahead, like I normally do in class, I'm going to go through the steps, the 4 or 5 steps that this is going to look like, a brief explanation of the formula, and then we'll go through the example. And I would encourage you, and I'll mention this again, once we get to the example, if you could actually take out your calculator and go through the process yourself. Pause it, whatever you need to do to make this the most sense. Okay, so let me just run through this real quick. So, step 1. You're going to be asking yourself 2 questions here. Is it a left or right tail test? And all that's really referring to, we'll zoom in over here, is when you're asking yourself, and we'll go into this in the example, how is the hypothesis related to the mean? So we go back here. How is your hypothesis that you have related to the average of the mean? And over here in this sample over here, if say this is your mean, it's asking you if it's a right tail test or a left tail test, basically referring to whatever number you have on the left or the right. How these, for instance, is related to this one. So in this example here, we would call this a right tail test because we see that that number, this number right here, is greater than the number over here. So we're looking to the right of the normal curve. However, if we saw the number over on this side, we call that a left tail test. And it's always the relationship between the mean, number in the center, with the number you're looking at. And we'll do this again in the example. Just wanted to briefly look at that. So the example will be a little bit clearer. Okay. So now if we're to go over here, there's a formula we're going to use, and I'll go into detail what these all mean when we actually go through the example. This is the formula we'll be using. And you'll be basically be provided each of these little numbers in your question. You'll be plugging them in. So you're overall going to be using the z-score formula. So it'll be giving us that chart that we looked at before, this chart right here, at ztable.com. I'll have these links in the page, but basically you're going to be using this table to interpret whatever score you get from this formula. Okay. Step 3, plug in the numbers you get from the question. Step 4, this is where you actually look it up on the ztable.com. Your goal is to be looking up whatever number you get from this formula. And if you could look up here, you actually see that there's a z here. And that z is the score you're going to look up on the z-table. And 5, you're basically going to report the probability of how you got it, how well you did. So whatever number you get in that z-table, you're going to look at the percentage and compare it to one of these 3 numbers. These are called the alphas. It's just the name for them. And the alphas just refer to the chances that you got it wrong. So in this case right here, 0.05, 5% chance that you got it wrong. 0.01, 1% chance that you got it wrong, and this is 0.01% chance that you got it wrong. And it's just, this is your threshold, and we'll go into this in detail later, the threshold for your willingness and how much wrongness you're willing to have. So for instance, if you got your z-score up above, you're going to see if that number is less than the alpha. In this case, if it's less than 0.05. If it is, then you said yes. You're going to say yes, that's correct. However, if your z-score that you get is greater than 0.05, that's not okay. So it'll be an X. So and I'll go into more detail what that looks like. But basically, these alphas just give you a reference point for whatever score you get at the end to compare to. But we'll take a look what that looks like in an example. So I'm going to be using this example for California gas prices. So something we're pretty familiar with. But these questions, the reason I'm using this is these questions are very similar to the homeworks. They're basically the same idea, just with different numbers in them. So if you could kind of follow this through, you should be able to do the homework no problem. Okay? So let's first identify the hypothesis and null hypothesis. And we'll pull that up right here. So the question is California gas higher than the rest of the country? California gas on average is 278 compared to the rest of the country at 232. So the standard deviation of 0.17 and the n or the number of people in the sample. So the hypothesis, if you were doing this, if you had this research question, the hypothesis then that the researchers in this case came up with is California gas price is higher. So we see the 278, that number is obviously higher than the 232. So you're going to say, yes, California gas prices is higher. So hypothesis then is here that H1, that the California gas prices is higher than $2.32. That's the hypothesis. And the null hypothesis then, if you recall, null hypothesis had to do with relationships. So one, in the regular hypothesis, we see that, put an H here for hypothesis, we're saying that California gas prices, CA, is greater than average. So that's the relationship, is greater than. So the null hypothesis, H0, is that California gas prices are equal to average, A for average. So it's not saying that it's less than, it's just actually saying that if we were to look at the prices, maybe we chose a sample that happens to have really high gas prices. So in this example, the researchers actually went through and asked 100 gas stations, for instance, N of 100, asked 100 gas stations how much their gas prices were in California. And this, compared to the rest of the country, was much higher. Their average was 278. So the hypothesis test then is going to be seeing if we just happen to choose 100 very expensive gas stations and we just chose wrong. So kind of like in our example up above when we're talking about the students, if I chose 30 exceptional students that were really into school, they might say that their experience at college of the desert was better. So we want to make sure we didn't make this mistake in this hypothesis. So we're going to test it. So we're going to plug these numbers into the formula. And we will look down then. So step one, from up above, is this a left or right tail test? And as you can see, the 278 is to the right of the average of 232. So we're going to call this a right tail test because it's over here. Okay, so step one, it's a right tail test. Step two, we're going to use a z-score formula. So basically, we're using this formula here, and we're going to plug in the numbers. So So if you look ahead, and I have two ways you could look at this. Step 2, plug in the numbers. And these are all the numbers that I pulled from the actual question. But if I were to actually just zoom out a little bit, you'll see where I got these numbers from. So you could see that the 278, for instance, the sample mean is over here, 278. The standard deviation is over here, 0.17. The number of observations is 100. That's the number of gas stations that were asked. And the average mean was $2.32, which is right over here. So if you just look over here, you can see these are all plugged into the formula. And you can see here that the y is the sample and the z-score. So I plugged in the 278 there. And the 232 is the overall average. So you can see that here. And divided by the 0.17, which is the standard deviation, and the square root of the sample size. In this case, was 100. So go ahead and you want to pause here and take out the calculator to try to figure that out. And just make sure you're familiar with where all these are going to go. A common mistake is sometimes inverting, or for instance, like where I have 278 here for the California average, is make sure that the average of the sample, in this case California's average, is in front. And the overall average, the 232, is in the back. So just make sure you put the things in the right spot. And go ahead and try to mathematically figure this out. I'm going to pause it and do that. So it'd be great and important probably to make sure that you have this math figured out. This is essentially what we're going to be doing for all the homeworks. I'm going to go ahead and pause and take a look at that. And I guess just as a reference point, just always make sure you do the things in order of operations. So I'd recommend you, if you're having trouble with this, focus on the square root of 100 first. You want to get rid of the radical. And then go ahead and just, you did 278 minus 232. So we get the 246. And 0.17 divided by square root of 100. And I think with this one, when you run through the math, it might be a little bit off because I think they round too early. Like I think this 0.07 is going to be something different, whereas 0.02 is going to be something different. That has to do with estimation. So for the purposes of the homework, whatever you end up getting, make sure you don't really round until you get to the very last number. Okay. Go over here. So just as a double check here. So step 3 then. So you want to go check, step 3 is interpret the z-score. So this is where you want to go to ztable.com. That's easy enough to go look up, but this is where we go to interpret the score. So I'll show you how to look this up. So in this case, we got the score of 23, and this is just what we got from our formula up above. So what I actually do then is I'm going to go to the z-score table, and we're going to go through and look in this column, right over here. See where my cursor is. We're looking in this is the z-scores, like negative 3.4, negative 3.3, and so on. We want to go ahead and try to find the z-score of 23. So it's a positive number, and go down and down and down, and we see, actually it looks like it stops at 3.4, or a z-score of 3.4. And just as a reference again, when we look back at the normal curve, if we remember, I'll come back to this in just a second. Like the normal curve, if you recall, up at top here, with our little bit of a mess here, but if you recall here, normal curves usually only go up to 3 or 4 standard deviations. So when you get a really big number like this, in this case we were down here, and we got the number of a 23. Sorry, let's get up here. Down here, okay, a z-score of 23, very big number. It's a very high score. So recall the number generally goes up to 4. So basically when you get above a 4, the probability is very, very low. And I'll show you what I mean by very low. Because if you're actually to go look at these z-score numbers, if you remember, so for instance here, 3.4, you see that these are percentages. So this is 99.97%. This is 99.98% down here at the end. And that's a score of 3.49 is 99.98% of the curve. So if you're looking back up here, 99, almost 100% of this is full. And that's only with a z-score of 3.4. So basically what you're saying then is if you're going all the way up to 23, like they don't display it because at some point it starts to become absurd. The number becomes so small. So for instance then, if we're just back from the chart, we got the 3.49, and that equals 0.9998. Or 99.98%. So basically saying then, and what you always think about is, so this is the chance you got it right. So the error, the leftover spot from this is 100% minus 99.98. So you're left with down here is 0.002 error. So when you're up here, you're 99.98% sure you got it right. That means there's 0.02% chance that you got it wrong. This is the error. Or when you compare it over here, this is where you're going to look at this compared to the alpha that we got. So basically then, it's when you're looking at this chart, the Z table, you're basically looking over at these percentages on this end. And that's a chance you got it right. So you're always thinking then, what are the chances that we got it wrong? Here it's 0.02% chance we got it wrong. So basically then when you get big enough, so for any number above 4, so in this case, any time we're above 4, it's very likely that it's going to look like this. Your error, so if we were to calculate it like this, your error is going to look something like your probability is less than 0.0001. 0.001% chance you got it wrong. So basically then, anytime you give above 4, this is going to be your answer. This is going to be the probability that you got it wrong. We don't calculate it any deeper than that because it's so small that it's almost unimportant. So basically, whenever you get something that has a very high z-score, like this, in this case it was a 23, this is what your answer is going to look like. The probability is less than 0.001% chance that we got it wrong. Okay? So I want to highlight this because if you have a homework question where you get a very big z-score, so anything well above 4, so if you got a z-score of 5 or 6 or 7, anything above 4, your answer is going to look like this. It's going to be 0.001. It's going to look something like that. That'll be your answer you put in there. And it doesn't really matter how much bigger it gets because at some point it doesn't really make much of a difference. So this will be your answer. So what does this mean? Okay, so the final step is just interpreting this. Step 5, final step, goes back to that alpha reporting. So up above, when we talked about alphas, the question will generally tell you, and we'll actually go look at that. This question does not say, but if it doesn't say, we're going to assume an alpha of 0.05. And just as a quick reminder, traditional alphas are 0.05, 0.01, and 0.001. In this case, we just assume 0.05 if they don't tell you in the question. Just going back down here. So we're assuming a 0.05. So basically then we're asking, so we're saying, is the number we got, in this case 0.0001, that number less than 0.05. So 0.05 is the alpha, and that means the chance we got it wrong So basically I want to say, did the number we get with our formula smaller than the 0.05? We're allowing ourselves 5% chance that we got it wrong. So we want to know, is it smaller than, less than? So whenever your thing is less than, you could go ahead and say yes, with the number of 0.01, it's far less than 0.05, so we can conclude that we got it right. Or basically that it's very unlikely that we got it wrong because of how small that number is. So in a homework question, for instance, basically then they would ask you to enter probably into your p-value. So you put that 0.01 in. And for the final thing they may ask you, so can we conclude that we got it right? Or can we reject the null hypothesis? Is the other way they might say it. And this is where you would come to. So can we reject the null hypothesis? We would say yes, because the number was so small. So that's what all that's asking for. Okay? So basically that will be one of the problems on the homework. That's what it's going to look like. So just go through, and if you want to go back and look at that, and there's going to be a second version of that, which is what I'll take a look at right now. So type 1, and this will be type 2. And basically, this is looking at the same idea. It's testing our null hypothesis. It's seeing whether we got it right. But we're missing something key here. So this one is an example if you have no standard deviation. And remember, standard deviations are how we interpret z-scores. Z-scores. Sorry, my mouse is not picking that up. So basically then, our standard deviation is taking a look at z-scores, and if we don't have z-scores, then we're not going to be able to use the z-table, this one, to be able to get our percentage whether we got it right or wrong. So basically, the second formula is very same goal, but it has a few different things because we're missing the z-score. There's one additional step in the beginning. The difference is here, one additional step in the beginning. It has a slightly different formula. The main thing is going to be important. It has a different chart to look at. So rather than a z-score, we're looking at a t-table. So why are we doing this? Like I said, z-scores are based on the normal curve. So they're they require the standard deviation. And the standard deviation, if we're to look at this table over here, if you think of the standard deviation, remember we had the 1, 2, 3, 1, 2, 3, and we don't know what those are in this. So just like this picture depicts, we don't actually know what those numbers are. Okay? So what we have to do then is we have to make an estimate. So because we don't know about the ticks going this way, we end up estimating based on how tall the curve is. That's what these dotted lines represent. So we're essentially just going to estimate based on how many observations we have or how big our sample is. So like we learned, though the magic number for a sample size is 50, we also know that the more sample size we get, so sample, so the bigger our sample is, the bigger the sample is, the more accurate it is. So here, the bigger the sample, the more accurate it is. So we're taking advantage of that for this. So basically, we're going to be having a formula that's going to look at how big our sample is, and then is going to help us know how accurate it is, or basically like the last problem, the last formula, knowing how likely it is we got it right. Okay? So like the last one, I'm going to go through and show us the 5 steps, and then I'll go through the example. So here's just a quick rundown of what the steps look like. The main thing is, like I said, there's this early step in the meeting called degrees of freedom. And this is our estimate that we're using. It's a very, very simple formula. It's right here, and we'll look at it again in a second. But the degrees of freedom are simply n minus 1. And n is just the sample size minus 1. So you want to save that number because it's going to help us use the t chart. But basically, then this is where the bigger the sample is, the more accurate it is. Kind of referring to up here. So the bigger the sample is, the more accurate it is. That's what the degrees of freedom are. Okay, so step 2, you're going to plug in the numbers to the formula. This is what our formula looks like for this one. We're getting the t, and it's going to look very similar to the last one. There's just going to be no standard deviation. Just like the other one too, we're going to want to know whether it's a left or right tail test. Or we're going to look up, and then finally we're going to look it up on a t-score chart. So I have a link for that, and I also will have it posted down here, actually in this document. Step 5, you interpret it, okay? So let's go through this. So here's our formula then. So this is example 2. And I have the relevant things highlighted, which we'll take a look at later, and I'll also reproduce this question later on in the sample. So the researcher is studying earnings of women working full-time. This is a two-tailed test. This one, a two-tailed test is simply the same idea as a left or a right, only it means it could be both. So rather than left or right, it's both. So it's a two-tailed test. We draw a random sample of 280 women. So sample size is 280. We'll need to know that. Who earn a sample mean, so sample mean of 41,653, and a sample standard deviation of 29,563. And we also know the population, the average for everyone's earnings, is the 39,621, and the alpha is set at 0.05. So we'll need all these pieces later on. And I'll reproduce this. So degrees of freedom, step 1. We recall the degrees of freedom in this case. The formula is n minus 1. And our degrees of freedom here, our sample size is 280. And we can see that simply by looking up here, 280 women minus 1. So simply, our degrees of freedom is 279. So we're going to save this for future steps. So just write that down somewhere, keep it to the side, however you want to keep it. You'll need this later on. But we don't need it for the formula, but we need it when we look up the t chart. Okay, step 2. We're basically just plugging in the numbers from the question. So I'll zoom out a little bit here so we can see where these numbers are coming from. So here, it's simply taking the sample mean, so 41,000 right here. We're plugging that in, minus the sample, the population mean, 39,621, and dividing it by the sample standard deviation, right here, 29,563, divided by the square root of n, and n is the number of women. Okay? So if you want to pause that and go ahead and do the math, and just remember you probably want to do the square root first before you divide it. But you'll go ahead and you'll get something like this when you go through it. 2,032 minus 1766.73. And your final number will be 1.15. So again, I would try to enter that math yourself so you get familiar with it. But this number right here is your t. And I want to emphasize that this is t and not z, because that's a common problem, is if you look up this number on the z chart, you're not going to get the right answer. You need to look it up on the t chart. And we'll see what that looks like right now. So here's what we need. So let me look at this first, and then we'll look at the chart. So here's what you need to interpret it. So things you're going to need: the alpha, which is in the question this time, the degrees of freedom, which is from the first formula you did, and the t-score from the second formula that you did. So from the question, we know the alpha is 0.05. From our degrees of freedom formula, we know degrees of freedom is 279. And from that final formula we just did, we know our number is 1.15. So this is all going to be here on this chart. And I'll embed the link for this chart into the canvas, so you can actually look this up. This is just a chart off the internet. So here we go. Let's take a look at what this looks like. So here is your degrees of freedom chart. So as you can see then, we have a few things up here. Here's the one-tail or two-tail test. So these are the ones that some of the information you need. The other thing we see here are the alphas. So these are the alpha scores up on top. This whole thing up above are the alphas. And then this whole section here is the degrees of freedom. You can see the DF. So let me do a few examples of what this actually looks like. So in this case, from our information, we know we have the alpha of 0.05. So we're going to go over here, and it is a two-tailed test. Remember that is from the question itself. So we're going to be looking at this column, and we're going to go look over to the 0.05. So all the way down here, the 0.05. Okay. So we're the bottom half, and we're looking at 0.05, and we're going to scroll down based on the number of degrees of freedom that we have. And in this case, our degrees of freedom is 279. So you're going to see, zoom out a little bit, and I'll go through this again. Just do it once here. Our degrees of freedom are going to be somewhere down here, because you see here degrees of freedom is a 100 and 1,000. So probably just look at the 100 line. So we look down and we see where these intersect. So go follow this all the way down until we get to 1.984 about. Would be our t-score there. And the 1.984 is our threshold number that we're going to use. So we see then we have the number of 1.984. And what you're going to ask yourself is, the number you just looked up, in this case the 1.984, let me write this down here. The 1.984 is the number you got. The number we got from our formula, 1.15. Is this greater than or less than? And the goal we're looking for then is we want to make sure that the number we got is greater than the number we found. So the specific question you're going to be asking yourself, the number I got, 1.15, with the t-score formula, is this number greater than the 1.984? In this case, we see that it is actually not greater than. Therefore, we can't conclude that we got this one right. So, asking yourself, is the number I got, in this case 1.15, greater than the score you found on the chart? In this case, 1.984. And we say nope, it's not. Therefore, we can't conclude that we got it right. Or you might say we cannot reject the null hypothesis. So that would be our conclusion. If the homework is asking you if you reject the null hypothesis, in this case, you cannot. So for this one, your goal is always asking, is the number you got greater than the number you looked up? So let me just run through that real quick and how to use the t-chart. That's generally the questions we get for this one. Pull up this. Let me just erase this real quick. So this is just something you want to be careful with. Again, like I was saying, you want to make sure that you're using the correct chart for the question. Okay, so let's zoom in and take a look. So again, before you do anything, you want to make sure you're on the right columns. So all the things you're going to need are going to be in the homework question or whatever question you're asked. So in this case, the first question you're asking yourself, is it a one-tailed or two-tailed test? We saw from the question above, the two-tailed test. So we're looking in the bottom row. Bottom row. And then the second question you're asking yourself, step 2, is the alpha. In this case, your alpha is 0.05. So you're down here in the alpha, 0.05. So we know we're in step 1, one or two-tailed. Step 2 is what the alpha is. And then step 3 is your degrees of freedom. In this case, it was 279, which is closer to 100 on our chart here. And you'll see it doesn't matter too much how specific you are. So then basically you're going down this, all the way down until you find, you're going to stop at the number where you see 100. In this case, it's 1.984. And then that final question you ask yourself is the one down here. Which one of these is the number you got? In this case, we got the 1.15 from our formula. Is this number greater than the number we looked up? If not, then it's not big enough. So you're always asking, is it greater than? So in this case, we asked, is 1.15 greater than 1.984? And we could not tell. It was not greater than. Therefore, we cannot reject the null hypothesis, and we don't know if we got it right or not. So as far as next steps, I will go through and just take a look at these. The homework itself is basically going to be a z version, a z-score version, and a t-score version. And I would just be careful to make sure you're using the right chart and make sure you're using the right formula. So the questions are going to match pretty closely to these samples. So that's the first clue you might have. And the second clue is if you can't actually plug them in to the right formula. So for instance, if you try to plug in the t-scores example into the z formula, they wouldn't fit because you're missing the standard deviation of the population. So you want to go through and make sure you get these. And I guess also make sure you save the degrees of freedom from the t-score formula so you can look it up on the chart. And I'll just practice looking these things up. This t-score chart takes a little bit of getting used to, but it's not much different than what we've looked at before. A slightly different way of thinking about these things. So best of luck with all this. I'll go ahead and post this up and you all could start the homework.